Hello, this is video 50. We've been talking about conservation of momentum, and I've mentioned that we can use conservation of momentum for all collisions. So in this video, we're going to talk about one type of collision, which is called elastic collisions. The next video, we'll talk about inelastic collisions. So the way that elastic collisions are defined, well, first of all, momentum is going to be conserved for them, as it is in all collisions. But what's special about elastic collisions is that kinetic energy is also conserved. So sometimes you see the equation written out where it shows that the initial kinetic energy of both objects colliding equals the sum of the final kinetic energies. But I don't bother writing that equation because we never use it in my class, so I just don't want to add the extra confusion. But the idea that kinetic energy is conserved is actually an ideal situation, because if two objects physically actually collide and touch each other, then some energy is transferred to another form like heat and sound. So your kinetic energy is not conserved, it's transferred to a different form. But this is just an ideal type of collision where we assume that kinetic energy is conserved. So the types of collisions that will be elastic, either the problem has to tell you that it's elastic, or if it's billiard, right, or pool, then you can assume elastic collisions because there's such little amount of energy that is lost. So it turns out that if you combine the equation for the kinetic energy being conserved, and you combine it with the conservation of momentum, and you do a whole bunch of algebra, then you end up with what I call the shortcut equation, which is a lot easier to use than the one for kinetic energy. I'll just write it just in case you're curious. We're never going to use this one in this class, but I know some of you guys might be curious. I'm talking about the sum of the initial energies equals the sum of the final energies. Alright, so let's see here. So when you combine those two, you get this one. So when we are doing elastic collisions, we're going to use conservation of momentum, and we're going to use a shortcut equation, as long as it's a one-dimensional collision and it's elastic. So with that in mind, let's take a look at this example that I have, and this is the only example that I have for this video. We have a ball of mass m. It's moving in the x direction. This red one here collides head-on with a stationary ball of mass 2m. After the collision, the ball with mass 2m is moving to the right 2 meters per second, and it's telling you the collision is elastic. Find the initial and final velocity of the ball with mass m. Okay, so I added some paper here so we can have room. Let's write down our givens. For all collisions, as you saw in the previous video, I always write down the givens to keep track of all those different variables. So m1 is going to be my m. We don't have a number for it, but I just like to call it m, and m2 is the blue one that has a mass of 2m. And then I'm going to define four velocities: v1 initial, v2 initial, v1 final, and v2 final. There are four velocities here. So number one here, we don't know any of its velocities, initial or final. Those are the two things that we are trying to solve for. v2 initial, the blue one, we're told that it's at rest to begin with, so that's 0 for v2 initial. v2 final is 2 meters per second to the right, so it's positive. So those are all of our givens, and now we're ready to use our equation for conservation of momentum, and also the shortcut equation because this is an elastic collision. So let's write them down. So we have m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Let's go ahead and cross out what's equal to 0, the v2 initial. That means this whole second term here is 0. And We could plug in a number for V2F, but I don't really see the point since we don't have numbers for anything else. So we have two unknowns here. Whenever you have two unknowns, you're going to need two equations to solve for those two unknowns. So what I'm going to do is I'm going to use a shortcut equation. So the shortcut equation, I'm going to write it over here, is V1 initial minus V2 initial equals V2 final minus V1 final. And we can cross out V2 initial, that's equal to 0. So the shortcut equation has us already solved for V1 initial. V1 initial is equal to V2 final minus V1F. So the way that we're going to solve for our two unknowns here and our two equations is we're going to use substitution. Since V1 initial is already solved for, I can plug in V1 initial, which is V2F minus V1F. I can plug that in right here for V1 initial. So let's see what happens. You have M1 times V2 final minus V1 final equals M1 V1 final plus M2 V2 final. And now we have to do some algebra to get our unknown in this equation is now V1 final. We have to get it by itself. We have to first get rid of the parentheses. We're going to distribute the M1 here to both terms. Multiply it, so we get M1 V2 final minus M1 V1 final equals M1 V1F plus M2 V2F. So you get the terms that have V1F on one side, the terms that don't have V1F on the other side. So we're going to add M1 V1F to both sides. That's going to get rid of it over here. And then we're going to subtract M2 V2F from both sides. So on the left-hand side, we're going to get M1 V2F minus M2 V2F. We just subtracted it from both sides. So on the right-hand side, we'll be left with M1 V1F plus M1 V1F. Since those terms are the same, that means we have 2 times M1 V1F. And I know some of you guys don't like to work with variables, that you like to have the numbers plugged in, but sometimes you're going to be given problems that don't have numbers. So I hate to say it, but it's just algebra. Hopefully you're able to follow. So now we're still trying to solve for V1F. So we're going to divide both sides by 2M1. So to save a little bit of room here, I'm not going to recopy all of this. I'm just going to divide that by 2M1. So we have all of this equal to V1F here. So let's plug in the numbers. M1 was our ball of mass M. V2F was 2 meters per second, so times 2. And then M2 was the ball of mass 2M. V2F was 2. And we divide that by 2 times M1. M1 was the ball of mass M. So now you can see why they didn't give us the mass, because M is in every term, so you can cancel it out. So we're left with 2 minus 2 times 2, so 2 minus 4 over 2. So that gives us -1. So when that red ball hits that heavier blue ball, it's going to rebound and move backward. That makes sense. That's why the velocity is negative. And now we have to find the initial velocity of our mass here. Well, we can go back to the equation right here. We had solved for V1 initial. So V1 initial equals V2F, which is 2, minus V1F, minus a -1. So that means that V1 initial is equal to 3 meters per second. So that makes sense that that lighter ball had to be going faster in order to have enough energy to be able to move that blue ball, so that the blue ball ended up moving to the right as well. So this was just an example of an elastic collision. The most important thing to remember is if you are going to use that shortcut equation, make sure that the problem says it's elastic and make sure it's a one-dimensional collision. That's the only time you can use this. If that's not the case, you can still always use the conservation of momentum equation for all collisions.